So the first differentiation rule that we want to add to our list is taking the derivative of a logarithm. So if y is equal to the logarithm base a of x, then y prime is going to be equal to 1 over the natural logarithm of a times 1 over x. So we can prove this in a similar fashion to what we were using last time when we were finding the derivative of inverse trig functions. So if we rewrite our logarithm in its equivalent exponential form, we would get 10 to the y is, a to the y, because it's a logarithm base a, is the same as x. Then by implicit differentiation, we would take the derivative of both sides, so d dx of a to the y is equal to d dx of x. So the derivative of a to the y with respect to x is going to be the natural log of a times a to the y times y prime is equal to d dx, that was foreshadowing the future there, d dx of x is going to be 1. So then we can solve this for y prime by dividing by the natural log of a times a to the y on both sides. And we get y prime is 1 over the natural logarithm of a, and then I'll write it as times 1 over a to the y. And then using the same thing that we did last time, we can resubstitute out what a to the y is. So this gives us 1 over the natural logarithm of a times 1 over x, thus proving our theorem. So while differentiating a logarithm base a will happen, the corollary is probably the more important part of this, which is if we have the natural logarithm, so if our logarithm is base e, we get a nice reduction in that formula. So that is, if a is equal to e, we want to remember that the natural logarithm of e is equal to 1. So this gives us then that the derivative d dx of the natural logarithm of x is just 1 over x. So we will use that quite a lot. So one thing you will discover, the further you go in mathematics, the less you're going to see any other logarithms. In fact, in advanced mathematical books, they never use a logarithm of a different base. It's always the natural logarithm. And then to make things even more confusing, they start just calling it log instead of ln. So they just call, there's only one logarithm and it's log. So keep that in mind when you're reading math books. Sometimes when they say log, it doesn't mean common, it means natural. But for us, we will stick mostly with this formula, but we will from time to time see some other things. All right, so let's go ahead and use this to calculate a couple of derivatives. So our first one we have is x times the natural logarithm of x. So what rule are we going to need to use to find this derivative? Well, we have an x times ln x, so this is going to be product rule. And in our product rule, our f is going to be x, and our g is going to be ln x. So then our f prime is going to be, the derivative of x is 1. And as we just saw, the derivative of the natural logarithm of x is 1 over x. So then our product rule says y prime is g f prime plus f g prime. So g f prime, the natural log of x, times 1, plus f times g is going to be, or g prime, is x times 1 over x. So simplifying, we get the natural logarithm of x plus 1. So our derivative of x ln x is going to be the natural log of x plus 1 via our product rule. All right, so now taking a look at our next one, we have y equals the negative natural logarithm of the cosine of x. So which rule are we going to need to find the derivative here?
Is the cosine inside of something?
Yes, the cosine's inside the logarithm. Perfect.
The
Chain rule. Perfect. So this guy is going to be the chain rule, and we are going to have the following. So f of u is going to be the negative natural logarithm of u, and our u is going to be cosine x. So then by the chain rule, y prime is df du times du dx. So then we're going to have negative, and the derivative of the natural logarithm of u is 1 over u, times the derivative of the cosine of x du dx is going to be negative sine x. So negative negative makes it positive, so we get sine x over u. So then finally, to get back to our derivative, we substitute back out our u. So u is cosine, so we have sine x over cosine x, and sine x over cosine x is tan x. So the derivative of the negative natural logarithm of cosine x by the chain rule is tangent x. All right. All right, so to resolve our u trie, we identify our outer function as, once again, the natural log of u, and our inner function is x squared plus 1. So y prime is df du times du dx. So that's 1 over u times the derivative of x squared plus 1 is 2x. So that's 2x over u. And substituting our u back out, we get 2x all over x squared plus 1. All right. So we have a special case. If we have the logarithm of f of x, then its derivative is 1 over f of x times f prime of x. And this is really just the chain rule. Because if we recognize our inner function, f of u is just, as we did in the last couple of examples, the ln of u, and u is f of x. So then if we take our derivative, y prime is df du times du dx. So that's 1 over u times du dx, which is just f prime. But then u is 1 over, u is f of x, so it's 1 over f of x times f prime of x. So this special case comes up a lot. So it's a nice tool to have just memorized. If you have the natural logarithm of a function, it's just 1 over the function times the derivative of the function. And that's just the chain rule. It will save you a couple of seconds. If you just want to use the chain rule every time, you'll get the same answer. But notice if we recognize that for the previous problem, we have the natural logarithm of x squared plus 1. The derivative is just x squared plus 1 times the derivative of the inside, which is exactly the same answer that we got, right? So it's just a nice formula that will pair well with what we're going to be working on in a little bit. All right, so D let's go ahead and do this example. So using what we just saw, we can recognize our f of x as being x squared minus 2x plus 1. So then our y prime would just be 1 over the inside, so x squared minus 2x plus 1 times the derivative of the inside, which is going to be 2x take away 2. And if we want to clean that up a little bit, we can factor out a GCF of 2 out of the numerator, and then in the denominator, that actually factors into x squared minus 1 squared. So then we end up with just 2 over x minus 1. And that would be our derivative. But as mentioned in the past, if you just put that into WebAssign, that is also a correct answer. This one's just a little bit more simplified. All right, so now let us take a look at this next example. So example 2 asks us the question, well, how do we find the derivative of y equals the natural logarithm of x cosine x over the square root of x squared plus 1? Whew. So if we look at this, this is kind of looks really complicated. So let's enumerate what we would need to do. So the first thing we would notice is that we have a function composition, right? So our outer function is the natural logarithm of u, and then our inner function is x cosine x all over the square root of x squared plus 1. But then to take the derivative of u, u is a quotient, right? So inside there, we would need the quotient rule. So we would identify our f is x cosine x, and our g is the square root of x squared plus 1. But then, to find f prime and g prime, we would recognize that f is a product. So we would have to jump in another level, right? And inside this, we would have f is x and g is cosine x. And then we would recognize over here that g is a composition. So then we would have g of v is going to be the square root of v, and v would be x squared plus 1. So to brute force take this derivative, if we just started going forward, how many rules would we have to use?
3.
Yeah, we would start off with chain rule, but then inside the chain rule we would run into the quotient rule. Inside that quotient rule, I would run into both the product rule and the quotient rule again, right? So this is turning into quite an ordeal, right? We've got rules within rules within rules, 3 rules deep. It turns out with logarithms, there is often a better method than the full direct assault. So let's talk about, well, maybe we can use some algebra to make our life easier. So instead of the direct approach, let's use algebra to simplify. So specifically, we want to use log properties. So the ones that will be helpful are, we have our product property, And our product property of logarithms says if I have the natural logarithm of a times b, that is the same as the natural logarithm of a plus the natural logarithm of b. We also have our quotient property. And that says if we have the natural logarithm of a divided by b, this is the same as the natural logarithm of a minus the natural logarithm of b. And the last one we have is the power property. And this one says if I have the natural logarithm of a raised to the b power, it is the same as b times the natural logarithm of a. So using these properties, we can actually eliminate a whole bunch of our rules. So we'll notice the product property changes multiplication into addition. So that would avoid having to use the product rule. The quotient property changes division into subtraction, which would then sidestep the quotient rule. The power property is composition with a power function, and it changes that into a product. So we get rid of the chain rule, and oftentimes that exponent is a constant, and then multiplication by a constant, we can just pull the constant out of the derivative. So this will actually eliminate us having to use product rule, quotient rule, and chain rule quite often. Not 100% of the time, but when we take a look at our example, we'll see exactly how much work this will save us. So we have y equals the natural logarithm of x cos x over the square root of x squared plus 1. So the first rule we want to use is our quotient property. So if we use our quotient property, that is going to give us y equals the natural logarithm of x cosine x minus the denominator, the natural logarithm of the square root of x squared plus 1. So our quotient property said if I have the natural logarithm of a divided by b, it's the same as the natural logarithm of a minus the natural logarithm of b. So the next thing we want to take note of is on this one we want to use our product rule, or our product property. So in our first one, we have our a is going to be x and our b is going to be cosine. So we get y equals the natural logarithm of x plus the natural logarithm of cosine x minus the natural logarithm of the square root of x squared plus 1. So that was our product property. The next thing we're going to want to use is our fractional exponent. Plus the power property. So if we have a square root of something, what is that the same as a power?
1/2.
Yeah, so 1/2, right? Perfect. So then if we swing that exponent out in front, we get the logarithm of x plus logarithm of cosine x minus 1/2 the logarithm of x squared plus 1. So this is all algebra, right? We haven't done any calculus yet, but now we'll notice all of these are of the form ln of f of x, which we have a nice rule for taking the derivative, right? So our derivative now then is y prime is equal to 1 over x plus 1 over f of x, so cosine x, derivative of cosine is negative sine x, because that's our f prime over f, and then minus 1/2 x squared, and then plus 1, and the derivative of x squared plus 1 is 2x. So we clean that up a little bit. 1 over x. Sine over cosine is tangent minus tan x. Our 2's reduce out, and we get x over x squared plus 1. And so note, remember that the derivative d dx of the natural logarithm of f of x, as we saw above, is f prime of x over f of x. And we use that in all three of these. And by using those log properties, we avoided product rule, quotient rule, and chain rule. If you want to see just how much work that saved us, try to go back and do this the direct method approach. You will soon discover that it turns into a giant mess. And even if you do power your way through, which can be done, the end product looks terrible. It's just a big mess of stuff that needs to be simplified. So doing a little bit of algebra up front can save us a ton of work in the end. All right, so let's go ahead. The first rule we want to use is the quotient property. So if we use our quotient property, we get y equals the natural logarithm of x minus the natural logarithm of the square root of sine x. And that is going to be the same as the natural logarithm of the sine of x raised to the 1/2 power. So then by our power property, we have y is equal to the ln of x minus 1/2 the natural logarithm of sine x. So then finally we take our derivative. The derivative of ln x is 1 over x minus 1/2. And then we have sine, and then the derivative of sine is cosine. And cosine over sine is cotangent, so we get 1 over x minus 1/2 cotangent x. And that would be our derivative. So this one wouldn't be too terrible. We'd have to use the quotient rule and chain rule if we did it the direct method, but you'd probably get to the solution. All right. So we know when we have logarithms, that we can use our log properties to simplify products, quotients, and compositions. But now when I look at example 3, we want to do a little comparing and contrasting. And we're like, dang, well, this has got a lot of products, quotients, and compositions going on, but I don't have any logarithms, right? So we are going to use a technique referred to as logarithmic differentiation. The idea is there isn't a logarithm, but y equals is an equation. So the fundamental rule of equation says if I do something to one side, I have to do the same thing to the other side, right? So the idea with logarithmic differentiation is we know if we had a logarithm, it would make taking this derivative easier. So let's introduce a logarithm. So the first step that we're going to do is, one, we're going to take the natural logarithm of both sides. So that's going to give me the natural logarithm of y is equal to the natural logarithm of this whole thing, right? X plus 7 raised to the 13th power times x e to the x plus e to the x, all divided by x to the 22nd power sine to the 10th power of x. So now I do have a logarithm, right? So then step 2 is we're going to use log properties to expand all logarithms. But before we do, we want to take note of something. So if I look at this right here, what do I notice about this? I have x e to the x plus e to the x. I have a common factor of what in there? E to the x. So I can actually factor that e to the x out, and I get e to the x times x plus 1. So if we can factor something by turning addition into products, it will only make our life easier, because our goal is to use those rules for logarithms. We have a product rule, a quotient rule, and a power rule. So anything that can be rewritten as a product will make our life easier. Okay. So now that we have our product, let's go ahead and use some of our log properties. We're going to use log properties to expand. So the left-hand side is just going to stay as the natural logarithm of y is equal to. And we noticed when we do our log properties, things in the numerator end up being positive, and things in the denominator end up being negative, right? So writing this out, we're going to get a logarithm for each factor in the numerator. So I have the logarithm of x plus 7 to the 13th plus, I'm going to get a logarithm for my next factor, which we factored, natural logarithm of e to the x, plus a logarithm for my next factor, which is the x plus 1. And then for the ones in the denominator, the quotient rule says we subtract. So I'm going to get a logarithm of x to the 22nd power, and then minus another logarithm of sine to the 10th power. So the next rule we need to use is our power rule, right? So we have the logarithm of y is equal to, bringing our exponents out in front, And what happens with this one? What is the natural logarithm of e to the x going to equal to? Well, the exponential base e and the logarithm base e are inverses. So what happens? They undo each other, and what's the only thing that's left? Just x. Because they're inverses. And then plus, our next one, there's no exponent, so it just comes down exactly how it is. We bring our exponent out in front, so we get 22 times the natural logarithm of x. And then lastly, we bring our last exponent out, which is the 10 from the sign, and we get the natural logarithm of sine x. So now we've fully expanded all of our logarithms, and we're ready for step 3. And step 3 is going to be implicit differentiation, because we don't just have y on one side anymore. What do we have on the left-hand side? ln y. So we're going to use implicit differentiation. So now when we do implicit differentiation, the derivative of the natural log of y is going to be 1 over y, but we're doing it implicitly, so times y prime. Because whenever we differentiate y with respect to x, we always get a y prime. So then on the right side, we now have 13. The derivative of ln of x plus 7 is x plus 7, well, over x plus 7 times f prime, which is just going to be 1, plus the derivative of x is 1. And then our next one, the derivative is going to be, once again, 1 over x plus 1 minus 22 times the derivative of the natural log is 1 over x minus 10. The derivative is going to be over sine x, and the derivative of sine is cosine. So we get y prime divided by y is equal to 13 over x plus 7 plus 1 plus 1 over x plus 1 minus 22 over x minus 10 times cotangent of x. So then we solve for y prime by multiplying both sides by y. To get this. And then the very last step is we need to get rid of y. We don't want to have a y in our solution because we didn't have any y's when we started. So we just substitute out the original. So step 4 is we use the original equation to substitute out so we have then y prime is equal to y. Well, y was x plus 7 to the 13th times x e to the x plus e to the x all over x to the 22nd sine the 10th of x times what we just calculated, 13 over x plus 7 plus 1 plus 1 over x plus 1 minus 22 over x minus 10 cotangent x. So implicit differentiation gives us an alternate method to find derivatives that involve tons of products, quotients, and compositions. Once again, if you think that that was difficult, I implore you to go back to the original and just try to brute force it, right? So if we analyze this, if we wanted to take the derivative, what would we end up having to do? First rule would be quotient rule. Inside the quotient rule, I would have a product rule in the numerator, and inside that product rule, I would have the chain rule and another product rule, and then I would have to get into the denominator where I would also have chain rule and product rule, right? So you would be chaining into about 8 different derivative rules if you try the direct approach. Whereas doing a little bit of algebra, the derivative's pretty easy to take, and then you just back substitute out y. And one thing I do recommend is leave your answers like we did in step 4. Don't try to distribute and collect and do all that stuff. It just turns it into an unholy nightmare. So I know this is a little different. In all of our math classes before this, they're always like, simplify, 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 simplify. We're going to discover the further we go in this class, as I keep saying, simplification is relative to what we are trying to accomplish. So oftentimes in calculus, we'll just do something, and we won't simplify further unless we need to do something else, because how we simplify depends on what we want to do next. Because certain things are easier to use in certain forms, as we'll see. So a lot of the time we end up doing stuff like this, where we do a bunch of algebra to turn something from one form to another so we can do the calculus. So simplification is arbitrary in the sense, well, what's simpler? Well, it depends on what I want to do in the future. So we don't have this goal of just simplifying to something unless we have a reason to do so. All right. So now your turn. All right, so let's go ahead and find our derivative. So if we take the natural logarithm of both sides and use our log properties, we're going to end up with the natural logarithm of y is equal to, and I'm going to do all my log properties in one step. So I get 5 natural log of 2x minus 7 plus 2 times the natural log of 5x plus 1 minus the natural log of 5x minus 5, the natural log of 8x, take away 3, right? So this was, I did the product rule, the quotient rule, and the power rule all at the same time. So what is the net effect when we do this? Things in the numerator end up being positive. Things in the denominator end up being negative. And all of our exponents become coefficients on the logarithms, right? So instead of doing them one at a time, you can just write them all down in one fell swoop. So as a fun bonus fact, why are the ones in the numerator positive and why do the ones from the denominator become negative? So if we jump in our way back machine, what is a logarithm anyway? Well, we have a base 10 logarithm, but what is it that the logarithm is the inverse of? An exponential. So logarithms are exponents. If you have an exponent that's in the numerator, it's positive. If you have an exponent that's in the denominator, it is negative. Oh, that explains our signs, right? Because the logarithms are just exponents. So if you've ever wondered where all the log properties come from, they're actually just our exponent rules, right? Because if you multiply two things together with the same base, what do you do with the exponents? You add them. So when you multiply two logarithms together with the same base, what do? Oh, you add them. If you divide two things with the same base, what do you do with their exponents? You subtract them. Oh, we're doing the same thing. Logarithms are just exponents. The logarithms do whatever it is the exponents would do. If you raise a power to a power, what do you do with the exponents? You multiply them. So if you have a logarithm raised to a power, but the logarithm's a power, and it has a power, you multiply them together. Oh, that's why we multiply the 5 in this example is the exponent, and the logarithm is an exponent. So you multiply them together. All right. So now that we've done this, we take our derivative, which is y prime divided by y is equal to, we have 5, 2x minus 7 in the denominator. The derivative of 2x minus 7 is 2. So that's our f prime over f. 2 times f prime over x, f is 5 times 5x plus 1 minus the derivative of 5x is 5 over 5x minus 5 times the derivative of 8x minus 3 is 8 over 8x minus 3. So we get y prime over y is equal to 10 over 2x minus 7 plus 10 over 5x plus 1. Here the 5's reduce out, and we just get 1 over x minus 40 over 8x take away 3. And then we multiply both sides by y and substitute out our y. So y prime is our original y, so that is 2x minus 7 to the 5th times 5x plus 1 squared all over 5x times 8x take away 3 to the 5th times all this. 10 over 2x take away 7 plus 10 over 5x plus 1 minus 1 over x minus 40 over 8x take away 3. And that is our derivative. So once again, if you try to use the quotient rule directly, you'll run into the product rule in both the numerator and denominator, each of those also containing the chain rule. So you can do it that way, it's just going to be a bit long. All right. Example number 4, we want to find the derivative of x raised to the x. So this is an interesting function because it is a new type of function. And what I mean by that, the base and the exponent are both variables. So a polynomial or a monomial is something like this, where the base is a variable, but the exponent is a constant, right? And an exponential is something like the base is a constant and the variable is an exponent, right? And we have derivative rules for each of those. But now we have something new. Both the base and the variable are an exponent. So this is some new type of function. When we have this situation, we have to use logarithmic differentiation. So we're going to use logarithmic differentiation. So we have y equals x to the x, which is the same as taking the log of both sides. The natural logarithm of y is equal to the natural logarithm of x to the x, or the natural logarithm of y is equal to x ln x by our power rule. So then, to take our derivative now, we're going to need to use the product rule. So our f is going to be x, and our g is going to be ln x. So then f prime is 1, and g prime is 1 over x. So when we take our derivative, On the left side, we get y prime divided by y is equal to, our product rule is g f prime. So we get x ln x g f prime is ln x times 1. So we get ln x plus fg prime is x times 1 over x, which gives us the natural logarithm of x plus 1. So then solving, we get y prime is equal to ln x plus 1 times y, but y was x to the x. So our derivative of x to the x is the natural logarithm of x plus 1 times x to the x. It's an interesting little derivative. So if we ever have a variable in both the base and the exponent, we have to use logarithmic differentiation. That's the only way to do it. Because it's not a polynomial and it's not an exponential, it's something else.